So first question. In a compound, atoms of element Y form CCP lattice and those of element X occupied in 2 by 3 of tetrahedral void. That is the formula of the compound. Option X3Y4, X4Y3, X2Y3 and X2Y. So in these questions, look, atoms of element Y forms CCP. Which element forms crystal lattice? Y element forms crystal lattice and that forms CCP, and its number is taken as n. Number of atoms is n. And another element X occupied in 2 by 3 of tetrahedral void. We know if the crystal lattice is CCP, its number of atoms is n, then number of octahedral void is equal to n and number of tetrahedral void equal to 2n. So here X occupied in 2 by 3 of tetrahedral void. Number of tetrahedral void is 2n. Therefore number of X should be 2n. But its 2 by 3rd part is occupied. Therefore X is 2 by 3 into 2n. Therefore total number of X and Y. X 2 by 3 into 2. It is 4 by 3n and Y n. By simplifying we will get X 4 by 3 y 1. 3 multiplied by 1. X4 y3 is the formula of the compound. Therefore we can take option B is the right answer. Next question. If silicon doped with arsenic is an example of which type of semiconductors? P-type, N-type and P-type intrinsic. Semiconductors are two types, that is P-type and N-type. Here silicon is a 14th group element. That 14th group elements like silicon and germanium can be doped with 15th group elements like phosphorus, arsenic, and also can be doped by 13th group elements like boron, aluminum, gallium. So two type of doping are possible. This 14th group silicon and germanium doped by 15th group elements, that is first type of semiconductors, and also doped by 13th group elements, that is another type of semiconductors. If 14th group elements doped with the 15th group elements, it is called N-type semiconductors. These N-type semiconductors are formed by doping 15th group elements like phosphorus, arsenic. They have 5 valence electron. The silicon and germanium have only 4 valence electron. So they contains 15th group elements contain 1 extra valence electron. Therefore they are called electron rich impurities. Electron rich impurity. So by doping electron rich impurity, N-type semiconductors are formed. 13th group elements contains only 3 valence electron, which is 1 electron less than this 14th group elements. They are called electron deficient impurity. Electron deficient impurity. That is 14th group semiconductor doped by 13th group elements. That type of semiconductors are called P-type semiconductors. So two types of semiconductors are there, N-type and P-type. Our question is silicon doped with arsenic. Silicon doped with arsenic. Arsenic electron rich impurity. This type of semiconductors are called N-type semiconductors. So answer is N-type. Option B is the right answer. Next question. Which of the following FCC structure contains cations in alternate tetrahedral void? Option NaCl, ZnS, Na2O, CaF2. FCC structure contains cations in alternate tetrahedral void. So we want to check these ionic crystals. In these ionic crystals, cations are occupied at which of the voids? So first NaCl. Crystalline structure of sodium chloride is called rock salt structure. In rock salt structure, Cl minus ion forms FCC structure, and Na plus ions, cation, Na plus ion is present in all of the octahedral void. Here cation is in octahedral void. ZnS, zinc sulfide. It is called zinc blende structure. In zinc blende structure, S2 minus ion forms FCC structure, and Zn2 plus ion, cation, Zn2 plus ion is present in alternate tetrahedral void. Third one, Na2O. It is called anti-fluorite structure. Here O2 minus ion forms FCC structure, and Na plus ion, cation, occupied in all of the tetrahedral void. And last one is CaF2, called fluorite structure. Ca2 plus ion, cation, forms FCC, and F minus ion is present in all of the tetrahedral void. So here in NaCl, cation Na plus is in octahedral void. ZnS, cation Zn2 plus is in alternate tetrahedral void. So our question is, which of the following compound FCC structure contains cations in alternate tetrahedral void? So we can take option B, ZnS. Alternate tetrahedral void, Zn2 plus cations is present in alternate tetrahedral void. Next question. The ratio of Fe3 plus and Fe2 plus ions in Fe 0.9. Yes, options are given. So here question is the compound Fe 0.9 S1. So we can multiply this both elements by 100. We will get Fe 90 S100. Just converted into whole number. So our compound is Fe 90 S100. And this question can be done by two methods. In first method, it is a general method, most common method. So we know all ionic crystals have charge should be neutral. All ionic crystals charge should be neutral. That is, charge of cation should be equal to charge of anion. Here charge of cation, that is charge of sulfide ion, 2 minus. Total charge of cation 200. Therefore total charge of anion cation also should be 200. It is 200. Total charge should be 200, and therefore total charge of cation should be 200. That is, charge of cation and charge of anions equal. Charge of anion 200. Charge of cation, total charge of iron, 90 iron atoms are there, total charge of iron is 200. And this 90 iron contains Fe3 plus and Fe2 plus ion. We don't know how many number of Fe2 plus and Fe3 plus ions are there. So let us take number of Fe2 plus is X. Therefore number of Fe3 plus equal to 90 minus X. So we can write total charge of cation. Total charge of cation is charge of Fe2 plus and charge of Fe3 plus. So we can write it is total number of Fe2 plus is X into its charge. Charge is 2. And total number of Fe3 plus is 90 minus X into its charge. Charge of 1 Fe3 plus is 3. That should be equal to 200. By solving this is 2 into X, 2X plus 90 into 3, 270 minus 3X equal to 200. By solving X is equal to 70. That is the number of Fe2 plus ion. And therefore number of Fe3 plus equal to 90 minus 70 equal to 20. So by writing number of Fe3 plus and number of Fe2 plus are obtained, Therefore the ratio Fe3 plus by Fe2 plus equal to 70 by 20 equal to 0.28. So answer is 0.28, option A. This question can be easily done by another method. If we know the theory of non-stoichiometric metal deficiency defect, because Fe90S100 is an example of non-stoichiometric metal deficiency defect. Metal deficiency defect. So this FES, without defect we can write it as Fe100S100. It means no defect. Equal number of cations and anions are there. And that ionic crystals are just like this, which contains Fe2 plus ion and S2 minus ion. Fe2 plus, S2 minus, S2 minus, Fe2 plus, S2 minus, Fe2 plus, like it. Equal number of cations and anions are there. After the defect, some ion atoms are missing and its formula become Fe90S100. It is after the defect. So we know here 10 ion atoms are missing. Fe2 plus, S2 minus, Fe2 plus. So after the defect Fe90S100, some Fe2 plus atoms are missing. So this Fe2 plus ion is missing from here. So one Fe2 plus ion is missing. It is missing. To maintain electrical neutrality, nearest cation converted into higher oxidation state. So here two positive charge is lost. Therefore one Fe2 plus converted into its higher oxidation state, that is Fe3 plus. And here one positive charge increases. Another Fe2 plus also changes to its higher oxidation state Fe3 plus. So total two positive charge increases. So by losing two positive charge, here one positive charge, here one positive charge increases. Therefore electrical neutrality is maintained. Therefore we know if one Fe2 plus is missing, the crystal contains total 2 Fe3 plus ions. Fe3 plus ion is formed. Therefore here Fe90S100 total 10 Fe3 plus Fe2 plus is missing. Therefore 10 1 2, therefore 10 20 Fe3 plus ions are produced. Therefore number of Fe3 plus is 20. Number of Fe3 plus is 20. If we get the number of Fe3 plus ion, number of Fe2 plus will be obtained. If number of Fe3 plus is 20, therefore remaining number of Fe2 plus is 90 minus 20, that is 70. So we can write Fe3 plus by Fe2 plus ratio 20 by 70, 0.28. So I think this is the most easy method if you know the theory of non-stoichiometric metal deficiency defect. By missing one Fe2 plus, 2 Fe3 plus is produced. Electrical neutrality is maintained. Therefore total in Fe90S100, 10 Fe2 plus is missing, 20 Fe3 plus is produced. Number of Fe3 plus is obtained, therefore number of Fe2 plus can be calculated.